and welcome to today's flipped lesson. So I don't know about you, but even though it is way past Christmas time, I still have candy canes lying around the house. This is a whole candy cane, and for some reason this is only half of one. I'm not sure why we haven't thrown this one away. But if I ever just wanted to know how much candy cane I had all together, well, I could just take the length of this candy cane and put it together with the length of this candy cane, and then I would know the total length of candy cane that is in this house. Brilliant. That is called the segment addition postulate. Let's take a little minute to look at how that applies in your geometry course.
All right, here are the standards that we will be addressing today. There's a whole bunch of them in one of those things. And then we have these new leap evidence statements over here on the right. And so those leap evidence statements address several different standards. And so the congruence standard over here falls under that leap evidence statement. All right, so today's objectives are to determine the length of a line segment using the segment addition postulate, and then to do similar steps with angles, and then determine types of angles and then angle pairs as well. All right, so our first step, we are going to determine the length of a line segment using the segment addition postulate. All right, so here's our first postulate of many that we will see in geometry. Pause the video now so you can fill in your postulate tracker. So the ruler postulate says that you can use a number line to measure line segments. The length of a line segment is a distance between its endpoints. Pretty basic. So, for example, if we wanted to use the number line to find the coordinate point of U and the coordinate point of V, then find the length of UV, we could do that easily. So we see where U is. U is located at -7, and then V is located at +4. If we want to find the distance between them to find out how long the segment UV is, we could obviously count every single space that's in between. Or you could just take the difference of the two values. So we can do -7 minus 4, and we end up with a lovely -11. However, distance is always going to be positive. So we basically need to take the absolute value, that's what those bars mean, and the absolute value of -11 is just +11. So the length of UV is 11. Okay, the segment addition postulate. So what that means is that if you have one segment, one long segment, AC, and you have point B in between there somewhere, just random, then that means that you can take the length of this first piece and add it to the length of the second piece, and you will get the length of the whole piece. Makes sense. So here's an example where you would have to do a little bit of work using that knowledge. So it tells us that point F is just on that line segment EG, which we can clearly see in the diagram, and that EF is equal to 12 right here, and that FG is equal to 28. We want to find the unknown length EG. That's the whole thing. Well, we can see that if we take the length of the small segment and add that to the length of the large segment, we will have the length of the whole segment. So plugging values in, we just...
12 plus 28 is going to give us 40.
Okay, so here we have a little bit more challenging of a problem. Point Q is between points P and R. PR is 7x plus 10. Find the values of PQ and PR. PR is the length of the whole segment, and we are given the expression 7x plus 10 to represent it. So we can start out with the fact the segment addition postulate tells us that PQ plus QR is going to give us the value of PR. So now we can just plug in information we know. So PQ is 3x, plus.
QR is 18 equals PR, which is 7x plus 10.
Now we use some of our algebra knowledge to solve for x. I'm going to subtract 3x from both sides, and I'm going to subtract 10 from both sides.
So this is gone, and I'm left with 28 is equal to 4x, and the 10s are gone. Divide by 4 on each side, so we have 7 is equal to x.
Is that our final answer? No, it's not. We want to find the values of PQ and PR. So in order to find the value of PQ, we use the expression 3x. So since we know that x is 7, we just plug it in. 3 times 7 is 21. So PQ is 21. That's one of our answers. And then to find the length of PR, we use the expression 7x plus 10.
Since I know that x is 7, I'll plug that in. 7 times 7 is 49 plus 10 is equal to 59.
All right, our next postulate is the segment congruence postulate. That just states that congruent line segments have equal length as measured by a fair ruler and do not have to lie on the same line. So for example, we would identify segments that are congruent by tick marks. And so this segment BE has 1 tick mark, and the segment AE has 1 tick mark. So we can say that segment AE is congruent to segment BE. The symbol for congruence is a squiggle on top of an equal sign. Now the segment EC has 2 tick marks, and so that means it matches up with ED, who also has 2 tick marks. So EC is congruent to ED. Okay, now we want to find the lengths of the line segments. Now that we are told that AB is congruent to CD, we can mark that in our diagram. We want to use that information to help us find the lengths of those segments. So since AB, the actual segment itself, the bar on top means we're talking about the segment, is congruent to CD, that means that the length of AB, we denote that with just the endpoints, is going to be equal to the length of CD. So the bars mean it is the segment. No bar means it's the length of the segment. So now we can plug in the length of the segment. The length of AB is
5x minus 4, and the length of CD is 4x plus 8. So I'm going to subtract 4x on each side. I'm also going to add 4 on each side. So I'm left with 1x, or just x. These cancel as well, is equal to 8 plus 4, which is 12.
all right, so that is my value for x. But the question asked, find AB and CD. So the length of AB is 5x minus 4.
If x is 12, that means that it's going to be 5 times 12 minus 4. 60 minus 4, and 56 is the length of AB.
So CD is going to be 4x plus 8.
4 times 12 plus 8, 48 plus 8, and we get 56 is equal to CD.
All right, so next up is all things dealing with angles. An angle is a figure that is formed by 2 rays, called sides, that share the same endpoint. The common endpoint of the angle is called the vertex. So here in this diagram, the vertex is Q, and the name of this angle is angle PQR. That order matters. The vertex needs to go in the center. Angle PQR is made up of the 2 rays, ray QP and ray QR. So, for example, if we want to name the vertex of this angle, the vertex of this angle is V. The sides of this angle are rays VU and VW. Name the angle in 3 different ways. So we can name the angle UVW with V as the vertex in the center. We can also name it in the other order. We could call it angle WVU. V is still in the center. And because it's the only angle that's floating around in this space, we could call it just by its vertex, angle V. So let's try using a protractor to draw a triangle with the given angle measurements.
Okay, if you're going to draw a triangle, you can just start with one line on your paper, any size, wherever you want to put it. Boom, done. And then I'm going to label the end points A, B. Okay, it says next that the measure of angle ABC needs to be 30 degrees. Well, here's A, here's B, which needs to be the vertex of your angle. So that means that wherever we put C now needs to make sure that it's at a 30-degree angle from B. So we take the center of our protractor, mine has a little tick mark there, and we line that up directly with point B. All protractors are different. Sometimes this is a circle and this edge is filled in. I like mine because it's not filled in. Okay, so then I'm going to look on the protractor. We have 2 rows of numbers. You see that? The row of numbers is the one that starts at 0 where your line is. So my line segment is here, my point A, AB of the angle is right there. And the 0 is here. That means I'm going to use the inside numbers. Okay, so I'm going to go up till I find 30, and then I'm going to mark it right there outside the protractor. And then I'm going to turn my straight edge and connect B to that tick mark. Okay, it doesn't matter how long the line is, just make sure it extends fairly far. So the next angle is CAB. The reason why I chose that one next is because A is the vertex. And I don't exactly know where C is currently, because C is going to be wherever this segment and the next one intersect, and I don't know where that's going to be yet, but I do know that CAB needs to be 105 degrees. So since A is the vertex, I put the tick mark there, line up the straight edge. Since 0 is on the outside over here, I'm going to start on the outside and go all the way around till I get to 105, which is right there. Got the tick mark. Okay, and then I'm going to turn my protractor and I'm going to connect A with that mark up there. Now we can see I did not draw this segment long enough because they don't intersect, so all I have to do is extend it. And where they meet will be point C. Okay, so that intersection is there. And if all is done correctly, this angle should measure 45 degrees. So to check that measurement, with C as the vertex, I'm going to line it up, line up the straight edge with AC. Since AC is over here and the 0 is over here, I'm going to go on the outside. And if I come around, it lines up directly at 45. Really like 44 and some change, but for accuracy purposes, that's pretty good.
All right, get out your postulate and theorem tracker. The angle addition postulate says that if point D, right here in this diagram, lies in the interior of angle ABC, which it does, then the measure of angle ABD, that's this guy here, plus the measure of angle DBC, that's this guy here, if we add them together, we get the measure of the whole big angle, ABC. The angle congruence postulate says that if 2 angles have the same measure as measured by a protractor, then the angles are congruent. Also, if 2 angles are congruent, then they have the same measure as measured by a protractor. So it just goes in both directions. An angle bisector would be if you had a point out here, such as C, and if it bisected this angle B, that means that these 2 pieces would be considered congruent. They might just have one arc, or they might have an arc with one tick mark to show that they are congruent angles. Okay, so let's see this as an example. If the measure of angle ABC, that's this whole angle here, is 144 degrees, and the measure of angle DBC, that's this piece here, is 72 degrees, then find the measure of angle ABD. So this is our unknown right there. So I can see from the diagram that the two pieces of the angles of the whole angle can be added together. So the measure of angle ABD, our unknown, plus the measure of angle DBC will give me the measure of angle ABC. This is all proper notation. Okay, so ABD is our unknown, so we can stick an X in there if you want for easier work. DBC was given to us as 72 degrees, and ABC was given to us as 144.
So subtract the 72 from each side, and we're left with x is equal to 72. And remember, the x actually represented the measure of angle ABD. That's what we were looking for.
So it turns out that D gives us the angle bisector. BD is our angle bisector. All right, classify angles. We have acute angles that are less than 90. So that's the example here. We have obtuse angles that are greater than 90 but still less than 180. So that's angle B. We have right angles that measure exactly 90. That's angle C. And then straight angles measure exactly 180. Those are basically just straight lines. So that over here is line M. So let's classify some of these. Identify the acute, obtuse, right, and straight angles in the figure. And this is not norm for geometry unless you are told. If the angle appears to be acute or obtuse, they are acute or obtuse. So we can't normally assume these things unless we're told so. So in this diagram, there's lots of options. One acute angle could be angle WVX. That can be an acute angle here because it is very small, clearly less than 90. Obtuse, an obtuse angle, we could use this whole big one here, WVY. For a right angle, that has to be clearly marked with a box. The right angle is angle XVY. And then the only straight angle here would be UVY. You could also reference any of the segments individually, but as far as an angle goes, that's the only one there is. All right, angle pairs. Two angles are adjacent if they share a common side and have the same vertex and do not share any common interior points. So angles A and B are adjacent because they share this common side and this vertex. That makes them adjacent. They're just next to each other. Two angles are complementary if the sum of their measures is 90. So in this diagram over here, angle EFG and angle GFH are complementary because together they add up to 90. They do not have to be adjacent. These are also adjacent, but they don't have to be adjacent to be complementary. Two angles are supplementary if the sum of their measures is 180 degrees. So that's this example right here. See how these are not adjacent, but because 110 plus 70 is equal to 180, that makes them supplementary. And two angles form a linear pair if they have a common side and the same vertex, and their sides point in opposite directions. So that means that it is a linear pair is supplementary and also adjacent. Okay, we'll abbreviate adjacent with ADJ. All right, using the linear pair postulate, if two angles form a linear pair, then they are supplementary. Simply put. So lots of adjacent angles here. DEF is adjacent to FEG. As far as complementary angles go, remember those add up to 90, so it's that same pair. DEF, FEG add up to 90. Remember that supplementary angles add up to 180, so you could use DEG and GEH as an example of that. And that's also a good linear pair as well. All right, that's all for that objective.